Okay, so we started talking about delta F and delta G yesterday. We talked about the changes in Helmholtz free energy, and we talked about the changes in Gibbs free energy, because we said that those are the terms that are important for chemistry, and we have to understand those terms. So then we talked about how delta F is related to W, and we talked about how delta G is related to W, which is the work done. We also derive the thermodynamical potential for these delta Fs and delta Gs, and you are going to derive them in chemistry. However, you may not see how they were developed, so this was my chance to show you how these were developed. Then I started talking about thermodynamical potentials and chemical reactions. And we kind of stopped there, and we're going to start talking about them from here. So we said that the thermodynamical quantities, which is delta U, delta S, delta F, and delta H, are extensive properties, which mean that they change with the amount of material. So if you double your sample, your delta U, delta S, delta F, delta H is going to change accordingly. However, that is not something that we always want. So instead, we want to standardize our things, and we want to convert them into intensive property. So the way we do that is we define a specific state, which we call the standard state, and we define it for 25 degrees Celsius, 1 atm, and for 1 mole of substance. And we put a subscript 0 on top, and that is the difference between the extensive and the intensive properties. Okay. Then we started talking about delta H0 for exothermic reactions and endothermic reactions. We also talked about Hess's law, and we started doing this example. So I'm going to pick up on from. So moving on to day 3. We are going to start talking about thermodynamical potentials and chemical reactions. So we're going to continue that discussion. So are we ready? Here we go. So what is delta H0? Delta H0 is the intensive property at standard state of 1 atm for 1 mole of substance at 25 degrees Celsius. So if I was to write delta H, I will call this delta H the standard heat of reaction. And it is defined as the heat produced when specific number of moles react in a balanced equation. So as always, make sure that when you get a question that it is actually balanced. Now, there is another term that is called a formation reaction. It's given in 10.5.3 which is formation reaction. And I'm sorry if the chemistry people have seen these before, but just bear with me. So what is a formation reaction? Okay. A formation reaction is defined as a reaction in which the reactants are elements at standard state. And there is only 1 mole of product. So we call this delta HF0. And since there is only 1 mole of product, the standard heat of formation are usually written as heat produced per mole of product. Understand, if you have elements that are reacting, so for example, oxygen going to oxygen, its delta HF0 will always be 0. And we also did, everybody done with that? I want to remind you that we did this. We did this, which is important. I'm going to rewrite that here. So delta F0 will officially be defined as delta HF0. The heat or formation is officially defined as the sum of the coefficient times the delta F of the product minus the sum of the coefficients times delta HF0 of the reactant. So put this in a box. We're going to use that. So this doesn't make a lot of sense yet, so let's do an example.
Calculate the heat of combustion of CH4. CH4 plus 2O2 it goes to CO2 plus 2H2O, where all of the reactants and the products are in their gaseous forms. Given the heat of formation, delta H, do you want me to read that too?
No, it's okay, but given that the heats of formation are these, okay?
Yeah.
Now what it's asking us that we have to find the heat of combustion of methane, right? This is methane, right, guys?
Mm-hmm.
Okay, so we have to calculate if methane is burnt, we have to calculate its heat of combustion. And all of these products are given. So how do I do that? Well, I have this formula I can use. So what are the reactants in this case? And what are the products? These are the
products.
Excellent. And these are the okay. So now how do I find the delta H of this reaction? delta HF0 of this reaction. So I have to find the sum of the product plus the sum of the reactant. And this I have to do the coefficient times the delta HF0 and the coefficients times the delta HF0. So there are two products and two reactants. So if I do this big box here and this big box here, what are the products I have? I have CO2 and I have H2O. And what's the reaction? What's the reactant? I have CH4 plus O2. Okay, now what do I mean by coefficient? Pick out what is needed here to balance this equation. That's the coefficients that we've been talking about. So when I do CO2, what's the coefficient?
1, 0, 1, yeah.
1. We call it 1 mole. Got it? Times, what's the delta HF0 for carbon dioxide? Negative 110.5 kilojoule per mole. What is the coefficient for H2O?
2.
2 mole times negative 241.8 kilojoules per mole. Yes? Now, what about CH4? 1 mole times negative 74.8 kilojoules per mole. And what about oxygen? What did we say delta H was for oxygen? So it will still be multiplied by 2 times?
0.
Good. And then all that's left to do is multiply all of these numbers. So it'll be negative 110.5 kilojoules plus 2 times, someone come up with that number.
No.
Oh, sorry, it should be a minus sign in here. Nobody corrected me. Should be minus here, guys.
I thought it looked a little weird.
Yeah, it was. And then we will have again negative 74.8 kilojoules plus 0. Somebody give me a number for this. 2 times
483.6.
400.
Yeah, it's negative though.
83.6.
Yeah, but it's negative.
Negative. Right?
Nick said it first.
And whatever that number is that comes out is going to be the delta HF0 of the reaction. It'll be called the heat of reaction for the combustion of CH4.